So hi everyone. Thanks for joining today. So today we're talking about something I think it's pretty big milestone for condition monitoring. What happens when we add large language models and generative AI on top of what we already do? Because honestly, we've gotten really great at collecting data. We've gotten great at detecting patterns, triggering alarms, trending things over time, all of that. But the part that still doesn't scale is the decision making, turning all those signals into a clear, consistent, what does it mean and what we do next type of information really still depends on a smaller number of experienced people. And in parallel to these developments, in condition monitoring, of course, electrical signature analysis has really grown in popularity. And that was for good reason, of course, because it covers a lot. It covers electrical faults, mechanical faults, and even process-related issues. And it checks a lot of boxes if you are trying to build a sustainable predictive maintenance program. But here's the catch. The information comes from different worlds, right? So because it covers multiple aspects of condition monitoring, you need to understand electrical behavior, and you need to be comfortable with spectrum analysis for mechanical faults, and you also need to process context data such as flow and pressure and operating conditions, and to understand what changed and why it changed. And that's exactly where the generative AI actually starts to make a difference. So what I will do today is walk you through how generative AI fits on top of these tools that we have already been using, and actually not to replace them, but to help translate the evidence into something clearer and more consistent so that the reliability teams can scale without drowning in dashboards. And if you remember only one thing from this session, let it be this. We're moving actually from automated detection towards something that feels a lot closer to an expert level reasoning, available all the time, 24/7 when you need it. So if you look at what maintenance and reliability teams are dealing with day-to-day operations today, the message is pretty consistent. They'll say we've got more data than we ever had, and somehow we have less time to actually interpret it. And the equipment environment isn't getting any simpler either. So we've got VFDs, lots of swings around and remote sites, equipment that runs intermittently, so the signals don't stay clean and predictable, and everything becomes more dynamic. And so what happens is then there's a mismatch which keeps growing. So you have more measurements, more trends, more alarms, but not nearly enough specialist time to make sense of what it all really means. So, and that's where the risk shows up. So sometimes it is obvious one, you can miss an early warning and it turns into downtime. But sometimes it's the opposite problem. So you might end up chasing the noise, and you're burning your time and budget on the wrong thing. So that's really why this topic matters right now, and not 5 years from now, but actually now. So I'd like to frame the whole challenge of the industry pain points in 4 practical pain points, basically, because once you name them, you realize most of them are actually dealing with the same thing. So the first one is the data overload. Monitoring systems are doing exactly what we asked them to do, but they're collecting more measurements, more trends, and more spectra, more events. That's great, but the reality is now it's too much for a human to review this in a disciplined way. Nobody has time to sit there and scroll through hundreds of plots and dashboards every day. And even if you try, you end up focusing on what is the loudest and not what is the most important, not necessarily what is most important all the time. So The second one is the analyst shortage. A lot of people are experiencing this already. So people are retiring and moving into different roles. And replacing that skill set isn't just hiring someone, and it takes years to train new people and build that intuition to know, what is normal for a specific site or a specific applications that you're managing, and what a real fault progression looks like, and what a process change looks like. So, and that experience is hard earned. So, the third pain point is the inconsistency. And I think this one is underestimated because you can have two really smart or multiple smart engineers look at the same evidence and still disagree. One person calls it misalignment, another one calls it unbalance or looseness. So one says monitor, the other one says schedule maintenance. And sometimes they're both reasonable. They're just applying different mental models. But for an organization, uh, this inconsistency becomes a problem because it means actions aren't repeatable and results depend on who happened to look at it at that particular time. And then the fourth one is cost pressure. Everyone is being asked to do more with less, more assets, more locations, and more variability, but fewer resources and fewer specialists and less time to investigate. So that pressure doesn't just affect budgets, it affects behavior. So teams either become overly conservative and chase every alarm, or they become numb and start ignoring warnings. So when you put these four together, the question isn't, can we detect faults? But the real question then becomes, how do we keep the quality of expert judgment, which is the reason in part, but make it consistently available across the whole fleet that we're managing? So here, I think it helps to zoom out for a second because condition monitoring has really evolved in layers. At the beginning, it was mostly manual checks, walk-arounds, listening, temperature guns, and basic inspections. Very experience driven, but also very limited. So you only see what you check, and you only check it occasionally. Then we moved into portable tools. That was a big step forward because now you could collect real measurements and compare over time, but it was still periodic. So, and you'll capture a snapshot, then come back a week later or a month later and take another snapshot. This is really still a very good and valid approach for semi or less critical assets where you don't really need 24/7 monitoring. And after that, you have online systems coming into the picture, which is really good and necessary for critical assets. So which changed the game. Now you've got continuous visibility and trends and alarms operate in context. You're not really waiting for the next route to find out something is wrong or something is drifting. And then the next layer was the one that we implemented, the machine learning and automation. So where the system really helps detect patterns at scale, it can flag changes faster, spot repeats, and track trends across a fleet without someone staring at charts all day. And here now we are at the next step, what I call moving from automation to intelligence. Because detection alone isn't the end goal here. The real value is when the system can help answer the questions people actually ask in the field. Okay, so something changed, but what does it probably mean? Is this important, or is it just an operating noise? What is the most likely cause, and what should we do next? Monitor it, verify it, or we should plan maintenance or act immediately. So this is not just about saying something change, but it's about explaining why it matters and translating that into action someone can actually take. All right, before I go any deeper, I want to do a quick reset on the terminology here, because as most of you really appreciate, AI gets used to mean 100 different things nowadays. So when I say AI, I mean the broad umbrella which is systems, that can do things we normally associate with human intelligence. Pattern recognition, decision support, sometimes even a form of reasoning. And just to be clear, the goal here is not to replace engineers. That's not the point. The point is to take the mundane and repetitive, time-consuming part of analysis, which is reviewing the same type of evidence over and over again, and turning that into a decision support so your experts actually can spend their time on the hard calls or the edge cases and the high-risk decisions. The other important point here is that AI is not the same as generative AI, and this is a very important distinction. So generative AI, or Gen AI nowadays, is one category under that umbrella. So it's powerful, and it has to be used the right way. And this works best when it is grounded in real signals and structured indicators, not just free-floating text. So in this webinar, when we talk about Gen AI or generative AI, think of this as a layer that helps translate evidence into clear explanations, but it still needs solid measurements and diagnostics underneath it. In condition monitoring, it helps to remember that AI isn't one single thing. It's really a stack of layers that work together. And remember, we're not talking about Gen AI here, it's the AI, that was the broad umbrella. So at the base, you have the machine learning. That's the part that's great at recognizing patterns in data. And within that, you usually see two flavors, which is what we employ and deploy in our systems. Supervised learnings, where you are training the system to spot the known fault types. And basically, we've seen this before, label it when it shows up again. And unsupervised learning, which is more about learning what normal looks like. And for this, the asset in this operating environment, and then flagging anomalies, when it starts drifting. Then you've got digital twins, which adds another dimension. That's where you combine physics with data-driven models. So you're not only seeing that something changed, but you have a model of how the equipment should behave under certain conditions. Of course, this is the foundation of our online solutions using the electrical signature analysis. And then on top of all of this, you've got the newest layer, which is the generative AI or LLM layer. This layer is different because it can interpret the outputs of those systems and connect the dots and produce explanations that sound much closer to an expert reasoning and what it likely means and why it matters and what to do next part. And the key message here is that these are not competent methods. You don't pick one and throw the others away. They are complementary, and the best results come when they're working together. So machine learning, which was the first layer, is something we actually have been using in condition monitoring for a long time in our systems. It's worth saying that it does several things extremely well. It can detect anomalies early. It can recognize repeating patterns in signals, and it can track fault progression over weeks or months, and it can constantly compare today's behavior against learned baseline. And even when the equipment has a lot of operating variation nowadays with VFDs and log changes and fluctuations. So in practice, our machine learning-based system already automates a big chunk of diagnostic workload. And of course, for those of you who are familiar with our systems, you would know that a lot of analysis is already automated, and you have the categories of different faults into certain categories so that you actually know where to look at. So they help you sort through volume and highlight what is changing and point you toward the asset that deserve attention, which is a huge win, of course. But there's still a limitation, and you've probably felt this if you haven't looked at our system in a lot or thought, okay, I'm seeing a problem and I know, okay, it's a transmission problem or foundation wasn't so bearing, so what? Machine learning is often very good at telling you again what is happening, but this looks abnormal, and again, this resembles a bearing pattern, and this is a trend and worse, but it doesn't always tell you why it is happening. So, and what the likely mechanism behind it. What is the next action type of information? So, and it gets you to the right evidence faster, but it doesn't, again, always close this loop into a clear explanation and decision someone can act on. And you would often need, a manual look into all the data to come up with something more precise. And so now, of course, the digital twin approach here, which is the second layer, was the pretty simple because it's all about expectation versus reality. So you build a model of how a motor, a pump, or a fan, or whatever it is that you're monitoring should behave under normal conditions, and then you continuously compare that expected behavior to what you are actually seeing in real world. And instead of only asking that something really change, you are asking, is the equipment behaving the way it should right now? And then when there's deviation, you can often catch it early, whether it's something electrical or mechanical, or even sometimes something driven by the process. And that's why digital twins are really strong for early warnings and for understanding the trend direction. And of course, for those of you who are familiar with condition monitoring, trend is the most important indicator in condition monitoring, so that you can see the drift before it becomes a major event, and then you can see whether things are stabilizing or getting worse. But even with that, there's still a gap. A digital twin might tell you deviation detected, and here's a problem, but that's valuable. It doesn't always finish the story. You still often need an expert to translate that into, here's the most likely mechanism, and here's what's happening, and here is what we should do next. So even with the machine learning and digital twin models that we are using and some other technologies are using, there is still a missing piece, and most teams feel it in the moment they try to scale. So machine learning is great at detection and classification, but it usually doesn't explain the root cause in plain language. It might also flag a pattern or label fault type. It doesn't naturally tell the story of what is driving it. So it also doesn't automatically combine multiple signals that our electrical signature analysis-based solution generates into one narrative, meaning that you will have sometimes, mechanical issues. You would see bearing fault, but if that comes from fluting, which is caused by a VFD, so it requires a more comprehensive look into multiple data sources to, again, create a single narrative. In real life, you're not looking at one trend in isolation, so you're looking at spectrum, operating conditions, load changes, and process indicators all together, trying to connect them into a single coherent assessment. Then there's context. So this one is very important too. Plants aren't clean lab environments, so you've got different operating modes, different process demands, and different maintenance histories, and different applications. So pumps, compressors, they're all different, and traditional models don't always adapt smoothly to every situation without additional tuning. And finally, it doesn't remove the need for expert judgment, especially when you're dealing with hundreds or thousands of assets. So the experts are still the bottleneck because someone has to interpret, prioritize, and communicate what matters. And that's why generative AI makes such a big difference, because it can sit on top of those layers, which is the machine learning outputs, digital twin deviations, operating context, and translate them into something closer to how an expert would explain it, what it likely means and why it matters, and how confident we are, and what is the next best action is. So here, of course, generative AI isn't just another algorithm you bolt onto our system. We bolt onto our system. It's a different kind of layer because it's built to understand, interpret, and explain, and not just detect. And the easiest way to explain this or picture this is think of it like having a reliability engineer or diagnostic engineer available 24/7. Not someone replacing your team, but someone doing the repetitive part that eats up time. So the part where you scan through evidence and figure out what is relevant. So instead of giving you another chart or another alarm, generative AI can review what the other layers are already producing in trends and PSD data, learn baselines, fault indicators, and translate this into readable assessments. So it can also help with the next step questions, which is where teams often get stuck. Is this likely or a real thing or just operating noise? And what is the most likely cause of this problem? And what should we do next type of thing? And of course, the big advantage here is scaling or the scale, because human expert can do all these things really well, but they can't do it for thousands of assets, across multiple sites every day without becoming the bottleneck. The beauty of Gen AI is it can provide that first pass expert style interpretation instantly and consistently across the whole fleet. So your specialists spend their time where it actually matters. The tough cases, the high risk decisions, again, or the actions that prevent downtime. So this is where the large, again, language models bring something genuinely different to the table. They have a few strengths that are pretty unique. First, they understand the natural language, which sounds obvious, but it matters a lot because it means that the systems can communicate in the same way that your team already works, emails, maintenance logs, not just the charts. And second, they can reason across multiple data sources. In real investigations, you're never looking at just one signal. You're combining all the trends, spectrum data, operating states, electrical values, process values, and maybe some maintenance history, and trying to build one consistent picture. And LLMs are designed to do that, and connected dot works. They're also good at spotting the connections and contradictions. For example, if one indicator suggests mechanical issue, but operating context suggests a process change, it can surface that and confidently pushing the interpretation into correct one. Another big strength is that they can summarize long time periods and tell you or compress that information into here's what changed, when it changed, and how fast it is progressed. And of course, you can do this manually as well, again, if you know what you're looking at. But as we mentioned, this becomes automated by the Gen AI, and it easily becomes scalable. And additionally, of course, they can produce explanations in a way that any engineer can understand, not just one person who lives inside the spectrum plots all day. So that's a big deal, because for non-trained eyes, this is very important. So you can just read and understand in simple, plain language that what's wrong with your answer. So when you put all of that together, that's really what moves condition monitoring from a simple automation to something closer to an intelligence level. We detected something and we understand the context, and here is, what is the likely cause of that and what we should do next. So now we've covered a lot of, the theoretical stuff. So let's look at how this all comes together and fits together in our electrical signature analysis solutions. So we collect the data, which is electrical signature analysis, of course, so meaning that we collect voltage and current, and from the motor control center without needing any additional sensors. And then with the help of machine learning and digital layers, that in raw signal, which is high frequency sample waveform data, converted into fault patterns, progression rates, confidence scores, and basically structured evidence or indicators. And then those indicators fed into the generative AI layer, And here is the key point that I want to emphasize. The LLM isn't sitting there trying to interpret the raw waveforms from scratch. That's not really the goal here. It's not the best use of generative AI. What it is doing is reading the structure indicators that our system already generates, again, by using all the raw waveform signals and then doing what a really good reliability engineer would do, which is interpreting all these indicators into a coherent story. What do they mean? And using the correct context, operating mode, load changes, recent events, and again, electrical mechanical parameters into one single cohesive output and store it. So once again, we're absolutely not replacing any previous layers that we're using, which is machine learning, digital twin. We are relying on those layers to create an easier to understand, more plain language results and reports, which is readable, repeatable, scalable across the whole fleet. Now, so probably by now the role of the LLM in our system is clear. It bridges the gap between the data and the decision, because patterns on their own don't create action. Spectrum peak, a deviation score, a fault label of transmission, misalignment, those are signals, but someone still has to translate them into what does it mean, how serious it is, what should we do next? Again, you can get some answers from the auto diagnostics still, but again, combining the context of the application, all the electrical parameters, process parameter is the key here. That's what the LLM is doing. It takes all those patterns and converts them into explanation. It doesn't just repeat an alarm, and it explains the logic behind it in a way what makes sense to the person receiving that information. And the outcome here is really the scale. It expands the ability of a single engineer to cover far more assets, hundreds, even thousands, without sacrificing clarity. So your experts still make the final calls, but they're no longer stuck doing the same first pass interpretation over and over again. So now, to make this more concrete, of course, I'm going to do some live demos as well, but here are the kind of outputs that the system can produce, and basically instantly. So it can say things like misalignment pattern has been increasing over the past 3 weeks, and not just the alarm, but what is changing and over what time window. Pump efficiency is down about 12%, and most consistent with hydraulic restrictions. So it connects the performance indicator to a likely mechanism in plain language. You have rotor issues. It looks stable, but keep monitoring. There is no immediate action needed type of information. Energy waste identified. The motor appears to be underloaded, meaning that there is an optimization opportunity, so you can actually correct this. And of course, all of this information is also available in some dashboards and charts and numbers, but again, LLM outcome would be to just read this and okay, understand that I need to do some optimization because the load profile of this motor is giving us this output, which is to, there's some potential saving opportunities if we properly size this asset. So meaning that now you can automate that first pass expert style interpretation consistently, quickly, and across the whole fleet. So if you connect all this back to the earlier pain points that I mentioned, generative AI directly lines up with the biggest challenges in our industry very cleanly. So when you are dealing with data overflow, the answer is in, they'll look at more dashboards, or the answer is fully automated interpretation. The system reads the evidence and tells you what matters. And then when there's lack of experts, again, generative AI acts like a built-in subject matter support. So not replacing your specialists, but capturing the kind of explanation and reasoning that normally live in one person's head, but making that guidance available to a wider team. So when diagnostics are slow, the value is the speed. You can get near real-time insights instead of waiting for someone to have time to review and write up, what is it that they are seeing. And also, when reporting is inconsistent, Gen AI helps here standardize it, so you get reliable summaries in a consistent format with the same terminology, same structure, and same logic. So actions don't depend on what happened to be on the shift or who happened to be on the shift. And when scalability is a constraint, generative AI removes the bottleneck here. It makes it realistic for a small team to monitor the entire fleet, not just a handful of assets they had time to check this week. So this is the outcome, and this is how reliability teams become force multipliers, keeping expert level quality, but spreading it across more assets, more sites, and more people. And this section, actually, what you can ask is the chatbot type of interactive menu that's going to be available sometime next year in our online system. But as you can see here, so you will be able to ask questions and get answers, and interacting with that, you might be able to feed in more information into the system to get even more precise information, such as, what's your parent number, and what type of asset is it. If you didn't mention the specific transmission type, you can feed that information to get more accurate information. So now let's zoom back out, and we can see where we're heading towards here, which is an assistant that is essentially always on, and that can monitor the entire fleet for us continuously, and can diagnose issues quickly. More importantly, it can explain what it thinks it's happening, likelihood causes, what evidence supports that, and what to do next. So, and again, the key point here is scale. So you can scale it easily, very quickly, and make it consistent every time. So now enough theory here. Let's see what this actually looks like in practice. So what I'm going to do now is quickly, just to show you some couple of examples from our actually portable tester, and show you some real life test results and all the different data sources that our reports contains, and then how this is translated with the generative AI. So let's give me a sec here. All right, so here I have a couple of reports that I'm going to go over, and then we will do live demo, which is going to be like a 30-40 seconds analysis by the generative AI, of course. And so the first asset is a compressor. But before that, for those of you who doesn't know what this report gives you, is actually it combines all the factors that I was talking about, all the layers, right? Foundation, looseness, transmission, all the mechanical fault detection done by the machine learning and digital twin layers. So you already have automation here, which tells you where to look at, whether your problems are electrical or mechanical. And also down here, you have all the electrical information, voltage, current, RMS values, power quality information, harmonics. You have your phase diagram, and you have your waveform, which is sampled at 10 kilohertz. So now, as an expert, I can look at here, and I can say, there is, not much going on the electrical side other than this, waveform, which looks actually horrible if you look at it. So just to make it even more clear, I can just zoom in out here, and you can see that how the tops are chopped, and there's a lot of harmonics inside that waveform. And mechanically, foundation, transmission bearing, and so this is a compressor, two-pole, 3600, VFD-driven asset. So now, what do I do with this information? So I already know that there's some electrical issue coming from the VFD, and I know that I have these 3 issues on my asset, on the compressor. I can go into Spectrum and look at here, and if I know how to do the spectrum analysis, I can do that. Of course, even you don't know anything, you can see there's a lot of peaks here, which tells you something, right? So if you know how to do the spectrum analysis, such as if you see 1x, okay, that's likely misalignment or unbalance. And if you see subsynchronous or non-synchronous frequencies, again, you have bearing issues or other issues, rotor stator. So each one tells you a story, but somebody has to do it. In this case, of course, you have a coupling. So this transmission means actually the problem is coming from the compressor side. So I know all this from my expertise. So, and you can become an expert, get the training and everything. So that's all, of course, very plausible. And also you can look at the electrical. Usually people's expertise, lie in one department. So you don't have multiple disciplines coming together. You're either an electrician or a mechanic. So then you do your vibration, and then the electrical data you see on this report doesn't really get translated into some useful information in many places that we're working with. So that's an issue. And I have low frequency, high resolution spectrum, high frequency spectrum. So what I'm going to do now is I'm just going to run the reports, which is going to do all that experts, manual analysis that, the SI expert can do, which, we have our distributors, our team here, and we provide the training, of course, to end users. You can learn it. There's a learning curve. But the point, of course, of this webinar is you don't need that anymore, because it's just going to be done by the AI, and it is done really well, I would say. So probably, if you actually are tracking the progress of Gen AI within the past 2-3 years, you can see how the models have advanced, and the same thing is happening here. Last year we were having relatively okay results, but now this is, because this is actually an agent we trained as we train like a human, and you can see now, okay, I have the report, right? So what I'm seeing here is that the executive summary, clear, plain language, it tells me that this compressor revealing mechanical electrical issues. The primary concerns are related to VFD, which shows clear signs of DC link capacitor degradation. Mechanical faults have been detected in motor bearings alongside with a loose foundation and developing issues within the compressor crankshaft assembly. While electrical parameters of unbalanced THD are acceptable, the identified faults require prompt attention to prevent a functional failure of the system. So, and the list of detected faults are here, VFD capacitor, because it came from the waveform analysis. Motor bearing faults, and of course, this is really actually pretty straightforward and easy one, but if you have the motor bearing information or the driven equipment bearing information, you have a database of 80,000 bearings inside the software. So basically you can scan all the fault frequencies for you. And it tells you have an in-race problem here, foundation looseness, and compressor mechanical fault. And if you want more detailed advanced analysis, here is the results of that: compressor analysis, bearing analysis, loose foundation analysis, and waveform analysis, which tells you, hey, here is your waveform clipping analysis, and that is related to the VFD issue that the system actually showed up here. And then electrical performance analysis is done, which also shows, if things are okay or something exceeds the limit. And then recommendation, so immediate actions: visually inspect the VFD for capacitor failure, and also inside and tighten the old foundation mounting bolts for the compressor. and also check the mechanical issues on the compressor side, short-term, long-term, and there's a conclusion here, which again tells you clear, actionable information. So that was the first report. Let me see what we're doing on time. So, okay, maybe I'll have some time on a couple more assets here. So this is a pump, VFD driven, and unlike the other one, this one is low voltage. This one is 4,000 volts. So it's a medium voltage system. I doubt this is VFD. The information might not be correct. So, but that's easy to understand. Actually, if I go here, look at the waveform, it doesn't look like VFD. So that VFD information is actually not correct. And coupling, because this is selected by the user. So if I look at here, I see a rotor problem. Voltage unbalance is unusually high. So that's 3. That's weird. Maybe some connection issues or the PTs are wrong, but that's quite high. And if I go into spectrum, I can see that there is actually a pole pass frequency here, but the low frequency analysis doesn't really do much for rotor issues. So you would want to go into high resolution spectrum manually, and I can also see those here as well. But again, the point here is let the AI do that for us, and so we don't have to bother with what the spectrum tells us. I mean, the bar graphs already shows, okay, there's a rotor issue which is close to red level on the bar graph. So, but let's see what the analysis is going to tell us. And sometimes the auto analysis might not accurately identify the severity of the problems. And oftentimes an expert looking at that and can see that difference or deviations, from the severity perspective, and still provide information. Okay, this is what I'm seeing. All right, so okay, the system indicates advanced rotor fault, and here is the detail of those pole pass frequencies, high voltage unbalance, which was already clearly visible to us as well, bearing and pump internal friction. So also, this is not something that you see here. It shows up as other because it's not automatically identified, but the report also tells us that. And again, immediate action. So the rotor problem is quite severe, actually. So that's why this analysis suggests that immediate action is should focus on the rotor. Of course, it tells us that investigate VFD output, but actually there's no VFD in my opinion here. So that's something, of course, as a bad input to the system. The Gen AI thinks it's VFD. I might be wrong, by the way. So, but that's what this is telling us. So overall, again, the same format consistently. It starts with the executive summary, give you the list of detected faults, explain them, and then gives you the recommendation and conclude the report. Maybe one more, we have time. Okay, what time is it? Right. So, okay, we still have 15 minutes. I want to leave some time for questions. So this is a belt and pulley system, low voltage, pretty straightforward here. So what we are seeing, quite a high current unbalance despite the low voltage imbalance. And let me see if, so this is also looking good. So it doesn't appear to be a VFD driven system. Yes, that's correct. And 1800 RPM. If I look at the spectrum, so what I'm seeing actually is clearly belt pass frequencies. So this was a belted application. These are belt pass frequencies, and there's some misalignments. Of course, you can see that that's actually just slightly here. So I would say the amplitude should have been here. So again, that's because this is a one-time snapshot, not continuous monitoring. You would have some sort of drift from the actual severity. Otherwise, you would see here, again, I can clearly see that that's actually quite high over here. So let's run the advanced analysis and then see the results. Again, it is taking 30, 40 seconds. So this is done in real time. And so that's why it's going to take some time to generate the report. And basically, what it does again, it is looking at everything that the expert analysis would look into VFD, look into the power values that we're seeing, the voltage current, RMS values, trending power factors, all that information, as well as, of course, the spectrum analysis of low frequency, high frequency, high resolution. So the first thing that it shows us, high current imbalance, which was 6. So we already actually have seen that over here, so which is correct. And you might notice a slight difference. So it says 6.11, but here it says 6.14. Actually, the reason for that is it takes the average of the 7-minute snapshot. So it's not just showing you the most recent data, but it's looking at the whole trend during the test period. So that's the reason for that discrepancy. Motor bearing. So naturally, if you have some belt wear and misalignment, you would see bearing frequencies, and you can actually do that analysis by yourself. So I would say this is the bearing frequency that the system picks it up from, and some over here as well. But again, you don't need to be that expert. So it's telling you that's the case, and it actually tells you the tri-event and non-tri-event bearings indicating the damage there, and actually lists you what harmonics that it's seeing those at the high resolution spectrum. Same analysis for belts, and belt wear was clear again from the spectrum and misalignments, and high level of electrical performance analysis is giving you an indication that you should invest the current on balance and inspect the belt drive system. So maybe one more here. So we have another, we don't have time, so I should probably stop here. But for those of you who want to try this out, we are going to release this feature, for those of you who has the AMD and the cloud use. So you will be able to try it with your own data and then see how it performs for you. And the results are, of course, they will speak for themselves, but it's pretty good. So let me go back to the presentation real quick, and then we'll close this and then get some questions before we run out of time. So, okay, let me just. Okay, so what this means for plants, again, it means you have fewer surprises because issues get explained earlier, and therefore you have less unplanned downtime, and you're not caught by surprise. It means, of course, a lot faster decisions. As you can see, analyzing one report takes only 40 seconds. But most importantly, the expert level diagnostics become available across the fleet, not just for the critical FIV asset, that get reviewed by the most experienced people, but every asset get the same treatment. So get a clear, consistent explanation, and what you should do, and what type of time frame you're looking at. So, and this is really what the AI gives you, that scalability. Efficiently, consistently across all the assets that you're monitoring, whether with the portable or online systems that we are providing. And one final thing that I want to mention before we get into Q&A session is that the beauty of electrical signature analysis, or the advantage that it has now, is that it's pretty much covering everything that you would expect to find on your rotating asset. You're not narrowly looking into one particular field, but you're looking at all the power circuit, power quality, you have transformers, VFDs, and then the whole machine train across the boards with issues on the compressors, on the pumps or fans, and now pump efficiency, including all the mechanical faults, and then process again, such as issues on the efficiency side. especially what we have with the pump monitoring, and that information also used by the AI. So you will get a lot more comprehensive with an expert level diagnostic available 24/7 when you need it. And that's really the advantage of electrical signature analysis, which can give you all these different discipline information into one single platform. All right, so that's pretty much it. So let's get into some questions. We are short on time, but if we can't get all the questions answered right now, feel free to send an email to us, and then we'll get back to you. So let's get into the Q&A session. Let me see if we have any questions. And okay, so there's already some questions here. The first question I'm seeing here, how will the Gen AI be able to distinguish between the type of equipment? Will it have access to the design specs and digital twin, or will it just make the findings easy to understand? Very good question. So that's actually the context-aware information that the Gen AI provides. So if you say it's a compressor or it's a pump or it's a cooling tower fan, all this context matters, and the Gen AI can actually analyze this and knows what type of typical outputs or faults the system would generate. So that's why the Gen AI is actually able to distinguish between those. So providing that information initially and saying what type of asset is it, it makes the analysis even more accurate. So is it possible? Another question is, if possible, let you show a small program how, okay, I already showed that real time. Is this applicable for chiller systems? Yes, it is applicable for chiller systems. All right, so another question is, very interesting. The challenge for us is making technology understandable to all, as for every new person using the dashboards, they have to get trained. Yes, okay. Will the LLM develop a personality over time where it understands the project and therefore be able to give any user a summary on performance and site? Yes, of course, that's the, it's an evolving process. But yeah, ultimately, if you're tracking the progress of AIs, they are capable of understanding the context or the history of what you're dealing with. So it become much more tuned to what you are doing. And yeah, the answer to that question is yes, but not. It's going to take time, but we're getting there. There's another question. Which all the technology inputs is your software working on? Only vibration analysis or anything else? So I thought I pretty much covered this already. We don't use vibration. Our system is sensorless. We're using only electrical signals, voltage and current, and we turn the motor itself into actually a sensor where it gives you all your vibration information or electrical and process and pump performance monitoring. So that's why at the end, I mentioned the beauty of our system is capable of capturing all this information from different disciplines. You would normally use different tools to detect for. So is AI working with the same tools like a human can use, like spectrum overalls? Yes, exactly. The AI is using all the different tools, spectrum, electrical process data that our system, our machine learning, digital twin, layers outputs, and then the AI is making sense of all those as acting like a human expert. Basically, that's how it works. So does it report bearing lubrication faults? Yeah, it would say one of the, if it sees and understand the context in a potential bearing issue could be due to misalignment or lack of lubrication. Probably it would list those two potential as a root cause, not necessarily, as lubrication. Sometimes it does that, but of course, it will improve that analysis over time, especially, if you're repeating the analysis on the same equipment. Is this available on cloud only? Yes, it is available on cloud only because we're using an API. So the analysis is taking that data and using an API connection and provide it. So it's not on-prem. Another question, you're gathering raw signals continuously, then calculate all you need for AI input, so user does not have to be expert knowledge, what kind of spectrum he needs. No, everything is automated here already. I mean, before AI, everything was automated already. So our system was designed in a way that, actually you can hear right on this presentation, the goal was for the past 20 years, 25 years, is to simplify predictive maintenance. So we never really promoted any raw signal analysis anyways, but the LLMs is just takes it another to a new whole level, basically. Is it possible monitoring high voltage systems? Yes, it is possible. I have already actually shown some examples, and from 4160 6.6 kilovolt motors. So how accurate is this AI from previous version? The AI is currently, I would say it's around 80-85% accurate. Probably an experienced diagnostic engineer with 3-4 years experience, so he can detect easy problems really easily, and that the accuracy there is 100%. Like if you have simple misalignment bearings or fan issues, gearbox issues, pretty much spot on. But when you get into more complex asset, there, of course, the analysis is not as accurate. One reason being that you need more information about the application, and that's not always provided by the end user, and so that makes the analysis a bit more challenging. So the term garbage in, garbage out. So the more information that you provide to our system, the more accurate the Gen AI will be. But I would say the accuracy on simple fans, pumps, and all those it's pretty accurate and consistent. So can this detect pipe strain or any problems related to piping construction, like pipe and reflection? So this is an interesting question. So we are already estimating flow and pressure, and we do pump curve and pump performance monitoring. Currently, it's not doing that, but of course, future development will include this type of analysis. So that's basically where we are. And there's another question: what is the Fmax that the system can measure? So we are using 10 kilohertz sampling. The Fmax is 5 kilohertz for high frequency analysis. We have 3 spectrums: low frequency, high resolution, high frequency. Each one is targeting a specific type of failure types and covering a specific failure, similar to vibration analysis, but it also does electrical analysis, VFD, chopping frequencies, and all that. For portable unit, what would be the price? You have to contact the regional distributor. You can reach out to us. We will guide you to correct distributor in your own region. Can we do generator and transformer condition analysis? We can do generator. We cannot do transformer condition analysis. Can the AI tool adapt to continuous process change? Yes, definitely. So the question is, can this work on continuous, which is our EMCM solution? Yes, it will work. It is actually working. We're already doing the integration, and it will definitely work. Please send us the PowerPoint. Yeah, please reach out to us, and I will send. Is this report language English only? No, the report will be available it's just a translation right now. The AIs can translate everything into all the languages available in the world. So there's no language limitation. It wasn't integrated to all languages just yet, but it's just 1 hour job. These are the questions, and I pretty much covered everything. It's 6 p.m. here, so we are out of time. Thanks everyone for joining in. Again, if you have more questions, please reach out to us, and then we'll get back to you. And for those of you who are using this AMT, and if you have cloud access, we will give you an access to try this out, see it for your own assets, so you can be the judge of how accurate this is. And again, if you want to try this out, just reach out to us, and we'll help you and give you the correct, representative contact in your own region. So thanks again. Thank you everyone for attending, and we'll see you next time.